Okay, so hi, welcome back to my YouTube channel. So in the previous videos, or I guess the previous two videos, we proved, well, in the second part of, for the second video, which should have been the second part of the first video, but I wasn't able to splice them together, splice those two recordings together for some reason. So it ended up as two individual videos, but that's fine. In the second video, we rigorously proved the work energy theorem, but I left out a very important detail. I have a very important proof of some inequality. And oh god. Oh, I am so sorry. I forgot to probably bind my tablet settings. So I just need to. This kind of turned into a disaster already. Okay, I need to take a picture of this first. Okay. Oh god. Okay, here we go. I am so sorry about this delay. Okay, so in the previous video, we went over rigorous proof of the work energy theorem from physics, from mechanical physics, or from physics in general, I guess. But in there, I had to make this very, very important equality that really the entire proof, from then on, the entire proof is pretty, it's not too hard to come up with yourself. Especially if you know what the statement is, then you can probably reverse engineer what exactly you have to do. But basically, the statement that I made. Okay. Oh, I forgot to do something. So, the statement that I made is that if we're taking the line, vector line integral of a vector field over some arbitrary path C, then we can parameterize C as this function, and then it just then we can just rewrite this very vague statement, because we can't quantifiably do anything with just the statement that we're integrating over this path. Let's call it C. So this equality, which is that this integral on the left hand side equals this integral, and this is just a normal integral, it's not really a line integral. I mean, I guess. Actually, I don't know why I said that. So that doesn't really make sense. It's just an integral with respect to the parameter, which is t. And this intuitively is obvious because we can just rewrite this section as the derivative r over dt, and then we can kind of abuse of notation. We can just cross the dt's out, and we get the original statements, noting that dr is equal to ds. But as always, this, for some of you, this might not be necessarily satisfactory completely, or completely satisfactory. So this video we're going to go over rigorous we're going to go over the rigorous definition of the line integral, and then we're going to prove that this equality holds. So in this section, really what we're going to do is we're going to go over, where did my mouse go? Oh no. Okay. What we're going to do is we're going to go over two types of line integrals. We're going to go over scalar line integrals, and we're going to go over vector line integrals. And really in this, these two integrals are pretty similar. It's just that in the scalar line integral, we are dealing with a, as the name implies, a scalar function. So just for simplicity, I'll use a simple three-dimensional case from R2 to R. And then vector line integrals. Oh, in the case of scalar line integrals, what we're adding up is we're adding up all the z's, adding up all the f's over our path. And in the vector line integral, we're dealing with a vector function. Again, we'll just stick to easy case. So this would be in a two-dimensional plane, or you can represent this fully in a two-dimensional plane. Equals to a vector quantity, and I already messed up this. Oops. Okay, whatever. In this case, it takes it from R2 to R2. I mean, you could take it from anything to, like, you could also take it from R3 to R3, whatever. In this case, what we're integrating is really, we're taking, we're adding up all the dot products between all the f vectors and small incremental changes in ds. And ds in this case will be a vector quantity, because yeah. So what the previous video was really reliant on, what is directly applicable to that work energy theorem derivation, is the vector line integral. But we're going to just go over both of these for, why not? This is just a little note. This really isn't too important, but in what we're going to go over here, so here we're going to derive a formula so that we can take the nebulous definition of line integral, which is, just this. Actually, this isn't here, or this is vector line integral, or a scalar line integral. We're going to be deriving a formula for both of these in terms with the use of a parameterization to make calculation possible or much easier. But this is not the only way to reformulate these integrals so that we can do calculation of them. There is something called differential forms that can also be used to calculate, to equate this line integral to something else, so that you can calculate. You can actually do calculations, and it turns out, in fact, that approaching line integrals this way with differential forms is much more useful, because it generates this very nice theorem that you just would not be able to prove with the regular multivariable calculus, the vector calculus approach with parameterization. And the theorem that I'm talking about is the generalized Stokes theorem. And basically what this theorem says is that if you add up over some sort of area in any kind of space, or not any kind, but like some kind of nice space, like a manifold, you integrate over the entire thing. That is equivalent. No, sorry. That's not right. So let's say. So let me restate it. So let's say we have this space. We have a subset of this space that we want to integrate over. It turns out that integrating a large, quote unquote, large function over the boundary of this space is equivalent to integrating some sort of derivative of this larger function throughout the interior of this space. And of course, we have some specific cases. Some specific cases of this are seen in calculus and in multivariable calculus. So in AP calculus, for example, the obvious thing is the fun one for theorem calculus. In this case, the boundary is the 2 points, the 2 x points. You know, like a, b, that you take difference between. And then the smaller function is the derivative of the normal f. Of course, you integrate over the interior. You integrate over the interval a to b. You integrate over the interior of the boundary with respect to, well, no, integrates the smaller version, quote unquote, version of the larger function f, which is just the regular one-dimensional simple definition and like most generic primitive definition of the derivative. And then in multivariable calculus you have Stokes' theorem, but it shouldn't be confused with the generalized Stokes' theorem. And then you have, you know, like the divergence theorem, you have Green's theorem. And Green's theorem is really just like Green's theorems, there's 2 theorems, of really just 2-dimensional cases of Stokes' theorem and the divergence theorem. Well, I've gone on quite a bit of a tangent now, but I do not understand this thing called differential forms because I'm not a math major yet, but you would learn this. Characteristically, you would learn this probably in like second differential geometry course in college or university. So if you don't notice you're in high school, that's completely fine. Like if you're in high school, so you're watching this and you can actually understand it, then that's a pretty good job, man. But you don't have to understand what this is because I don't understand it either. It's called differential forms. If you want to go look at it, you can. You know, just go to Wikipedia page, something. This actually is one video that goes over the generalized Stokes theorem pretty well. In general, it goes over topics related to differential forms pretty well. I forgot the name of the video, but it was by a channel called, I think it was Aleph Null. So it was this, I think, Aleph and then Null. So if you want to check it out, you can. Probably like I'll put a link to the video in the description or something. Okay, that was a really massive tangent. It's been like what, 5 minutes probably? 4 or 5 minutes? Whatever. Let's start off with the scalar integral. So in the definition of the regular integral in in AP calculus or something, or like a calculus 1 course, if we want to do it rigorously, we have to partition the line that we're integrating over. In the case of calculus 1, it's very simple. It was just a straight line on the x-axis, so just partition it. But and I forgot to mention this partition will be of size n, so it'll be n points. But in this case, in the case of the scalar line, let's go. I should probably just write this down. We're similarly going to a partition, but it's going to be of 2-dimensional points. So like it's going to be of forms xy. So we're going to have a partition of xy x1, y2, etc., xn, yn. And we're going to have f of our, we're going to have our function f of x and y equals z be continuous, differentiable. This is probably a much like stronger, not stronger, actually that's a weaker version of this, so it doesn't have to be continuous and differentiable. Probably, you know, if you did this with like actual multivariable analysis, there's probably some weaker condition under which this following equality will prove to be true, but whatever. So over here, we're going over the definition of a scalar line integral. So we're going to partition our path C into these. We're going to so let's just say C, this is C. We're going to partition it into n points, whatever, and we're going to approximate. Well, and what we want to do over here is we want to sum up all the values of f over C, and to do this with our partition of size n points, this is simply given by and this is where xy is a part of. I mean, x asterisk y and y asterisk I is a part of. Similarly, y asterisk I is part of the interval between y and y I plus 1, and this displacement, this small displacement factor is given by, this is just Pythagorean's theorem. If you really like, you can just zoom in on one of these smaller partitions. We're going to have like this, and well, what I mean is, as if n is sufficiently large, we can reasonably approximate these partitions as just a straight line, where the height, this line will be of length delta si, and then we'll have length, you know, if we put it into the coordinates of the xy plane, we'll have width, change of xi, and height, change of yi, and change of xi is given by xi plus 1 minus xi, change of yi is given by yi plus 1 minus yi. So delta si is simply given by Pythagorean's theorem, roughly, when x becomes sufficiently large, of course. Of course, this approximation will get better and better and better as n becomes arbitrarily large, and so to notate that, we just put a limit on here. I should have put on the bounds of this summation. And this partition can be arbitrary. We can partition it however we want, as long as we have n points, and as n approaches infinity. And due to some theoretical workings in the back, this turns out, usually depending on if the function is nice or not, this is completely fine. We don't have to really worry about the details too much. Specifically, when it comes to mine, there's two more rigorous renditions of the Riemann integral. They're called the de Boer integral And there's another one that I cannot pronounce, and I don't really. It's called like the Stellagitses integral. The pretty much they're just dealing with some more subtle aspects of the Riemann integral that you do have to take care of for to have a completely sound theory of integration. And of course, there's a gigatrad uh, interpretation of integral, which is it's like objectively it's better than Riemann integral, called the Lebesgue integral. But you need to know some measure theory in order to like fully understand it. But in the mathematics literature, usually it's not the Riemann integral that is used; it's the Lebesgue integral. If you want to learn more about Lebesgue integral, I might do a video on it. Probably not because it's also measure theory. Like, I don't really know measure theory either, but there's some pretty good videos on it. I might also link some in the description if you're interested in it. So this is our definition of a scalar line integral, where we have a partition of c into n points, and we let n approach infinity. But the thing is that we don't really want to calculate this. Like, who wants to calculate Riemann integrals with the definition itself? It's a pain, you know. And this here, and also like we would have to we would have to partition it first, and then we would have to do all of this superfluous stuff. And then we can't really work with this thing on the right either, because C is like we haven't really quantified what C is yet. So we can resolve. It turns out that we can, as mentioned before, we can resolve this with the introduction of a parameterization of C. Pretty much what that means is this will always be true if C is nice. I know I'm using the word nice a lot. It pretty much like if C is smooth. I think the requirement is like C if C is analytic, but that doesn't really make sense. I'm not sure. Yeah. You would have to search that up for yourself. I'm sorry. This part is also not that rigorous either, but whatever. As long as our C is smooth, like globally it's smooth, except for like at some points where it might be where it might like suddenly change. In case it's piecewise smooth, we can always then find a parameterization in terms of T of C, where our parameterization is R of T, which equals to xt, which equals this right here. This is correct. Yes, this should be correct. And we're going to define 2 points, 2 points of T, where we define Ti such that RTI equals the start, the start of the path, which is the point x1, y1, and RTF equals the end of the path, just x and y, and it's this, yeah. So now we're also going to have to partition T as well. So how are we going to partition it? Well, we're just going to, let's see. We're going to define every point Ti such that RTI just equals to xi, yi, or that's equals xi, yti, so yi. And we're going to define t asterisk I, so such that r t asterisk I equals x asterisk I vector x asterisk I and y asterisk I. So am I still forgetting? Oh yes, and we're going to define delta ti. Oh, this is very messy. I'm very sorry about this presentation. Let's box everything. Delta ti will be defined as ti plus 1 minus ti. Very similar to our partition of C. So now we will be able to rewrite everything from the original definition in terms of functions, in terms of t pretty much. So automatically, using our previous definitions, we can state that so we can already resubstitute these values in f with their corresponding t inputs. But our real concern is how exactly we can rewrite this change in this delta s. So I'll make a new slide, call our definition of delta s I. So how exactly can we, of course we can, obviously, we can just already rewrite this in terms of t, just be pretty long, being like, but this isn't really useful because this doesn't really give us anything to work with. But it turns out that we can rewrite this into something that we will be able to work with much easier. And what we're going to use is the actual fundamental form of calculus, the mean value form. And in this case, we will have, in this case, there will exist some, oh god, we kind of messed up the definitions earlier. Okay, I'm gonna pull back what I said earlier. We're actually, oh god, this is kind of haphazard. We're actually going to define t asterisk I. So we're going to put another limitation on our partition, or the points that we choose from each interval in the partition. We're going to define t asterisk I such that by the mean value theorem, in this case we're just going to use the x function as an example. There exists a point t asterisk I such that it's the derivative of x at that point is equal to the change in x at the boundary, so that's just delta xi over the change in the inputs, which is just delta ti. So this is how we're going to define t asterisk I, and from that then from that we get x axis y and y axis y axis y asterisk I. And so we can isolate delta xi such that we get this. And then we just plug this in to the stuff above. We get delta si is equal to yes, I know I should have said this, but here it's here this is the case for x. The case for y is very similar as well. You know, it's just change of y is equal to just that. It's very similar, but it's literally the same thing pretty much. So fat that out of the way. Oh, I messed that up already. Sorry. So we're going to be able to rewrite our original definition of delta S in terms of this, and we can then pull out the delta t squared, and we get so if we put this back into the original definition of the scalar line integral, we get I think I went from using little f to big F, but you get it. It's whatever. Yeah, sorry, but I honestly prefer big F. I should have started with big F. I am running out of room. Oh no. Oh god. Oh no. This is not. Oops. This is I'll just write the TI down here. This okay. Whatever. Maybe I should rewrite this. Okay. Well, whatever. And using the definition of the Riemann integral, we can put this into integral form very easily. turns out that this redefinition of the scalar line integral is much easier to work with. And of course, we have our endpoint ti is just so that this holds true, and tf is such that this holds true. And don't worry about the fact that n will approach infinity. We defined xn and yn such that they're always going to be fixed. And I actually think this is the reason why you can't use the Riemann integral. Actually, I'm not sure. I think this is the reason you can't use the Riemann integral to do integrals that approach infinity, or like integrals that, you know, like from 0 to infinity on like the x-axis. You know. And then you instead have to use the limits. Yeah, that's one of the problems of the Riemann integral that the Lebesgue integral takes care of. But I don't know anything. I don't really know any of the details about that, but whatever. So rewriting all of that in terms of our parameterization R, we simply have this. And this is much easier to work with here. This is much easier to work with. Just to calculate stuff, right? So that's the quality for scalar line integrals. And vector line integrals are like, they're really almost like exactly the same thing. It's just that we have a different function. Okay, well, maybe I should say exactly the same thing. We have a different function and we have a different operation how we combine values of the function and the displacement, the small displacements. But really the idea is almost pretty much exactly the same thing. Again, we're going to partition C into endpoints. Kind of a vector f instead. Yada yada. And we're going to dot it with SI. In this case, SI is defined as, oops, nope, it's defined as a vector. And then, of course, we can do the same trick with the mean value theorem, and we can get that. So I should probably rewrite this. We can do the same trick with the mean value theorem. SI equals of course we have to also define our parameterization, which it is exactly the same thing as with the scalar line integral. So if you need a refresher on that, just go back. This video is already pretty long. I don't want to make it any longer. So using the same trick. Oh god. We just get this again, and then putting it back into the definition of the vector line integral, we get and then pulling out the delta ti from the re-representation of delta y. we get this, and then using the definition of Riemann integral, we get another very similar looking thing. Similar thing to the case of this with the scalar line integral. And just in this case, we have f as a vector, we have a function as a vector quantity, or the output of a function as a vector quantity. Oh my gosh, I can't believe I said quality twice. And then our displacement factor is not a scalar, it's a vector in this case, and then we combine these two using the dot product instead of scalar multiplication. Or I mean multiplication between two scalars. So but in the end, the result looks very similar. In the idea, the main trick, which is using the mean value theorem, is it's ubiquitous between both these two types of line integrals. So we can just rewrite this using our parameterizations. And this, we should probably finish this off. This equality, this theorem, whatever, I don't think it really does not classify as a theorem. Like it's whatever. This equality is what we used in proving the work energy theorem, which is what we did in the last video. So yeah, that's pretty much it, I think. I don't think I have anything else. Let me look through my notes. Yeah, I don't think I missed anything. I don't think we have anything else to do. Examples, yes, examples are very important. Like, you can watch this video, you can watch a dozen videos going over the video of it, but you won't ever have a true understanding of, you know, line integrals in general. You won't have an understanding of anything in mathematics in general unless you build up your intuition, like a working intuition of those ideas, with concrete examples. Well, this video is already like really long. I think it's like approaching 25 or 30 minutes now. Yeah, it's approaching 30 minutes now, I think. It's really long. I don't want to go into anything else. I don't want to do any examples because I also didn't think of any. But if you want some examples, there's a very good, it's actually two. There's two sources that are very good. One of them is called Paul's Online Notes. Paul, if you want to self-study some of this, like if you want to self-study calculus 1, calculus 2, calculus 4, Paul Online Notes are very, very good. Very, very good. I self-studied calculus 1 and calculus 2 using those two, using Paul's Online Notes. And then there's also another good source. It's the OpenStax textbook. I'll link both of these in the description. If you want any example problems, just go use those. They have many good, very good example problems. So oh god, okay, that's the video. Thanks for watching. Hopefully I'll see you next time soon. Yeah, it's kind of a pretty big gap between this video and then the last physics/math video. But hopefully I'll pick up the pace on them. And yeah. Well, have a good day, and if it's nights, whenever you're watching this, have a good night. You know, just have a good one, I guess. See ya.